Mixed exercise 5.01, its own forces and friction. A-level applied maths, year 2. We are going to answer two questions. Question 1. A particle Q of weight W rests in limiting equilibrium on a rough plane which is inclined at an angle theta to the horizontal. Prove that the coefficient of friction mu between the particle and the plane is tan theta. B. A horizontal force P is applied to Q and acts in the vertical plane containing the line of greatest slope of the inclined plane which passes through Q and towards the plane. If equilibrium is limiting with Q on the point of moving up the plane, find P in terms of theta and W. So for A, we need to do a sketch as follows. This is a horizontal and this is a plane which is inclined at an angle theta to the horizontal. And this is the particle Q which has a weight W which acts downwards as follows. Because the particle rests on a plane, there will be a normal reaction R which is perpendicular to the plane. The particle is said to be in limited equilibrium. That means friction will be acting. And normally, the component of the weight will act down the plane, and that means friction will act up the plane as follows. So these are the three forces acting on the particle Q. We need now to resolve all forces which are neither parallel to the plane nor perpendicular to the plane. The frictional force, F, is parallel to the plane, so we don't need to resolve that. The normal reaction, R, is perpendicular to the plane, so we don't need to resolve that one too. The only force that needs resolving is the weight W. And we can do that as follows. Perpendicular to the plane, parallel to the plane. And that makes this angle theta. And so we can now use SOHCAHTOA to resolve the forces as follows. W cos theta, which is perpendicular to the plane, and W sin theta, which is parallel to the plane. We can now write equations involving all these forces. The first equation will involve R and W cos theta. And because the particle is neither flying off the plane nor going through the plane, we can conclude that R is equal to W cos theta. So R is equal to W cos theta. The forces acting parallel to the plane are also in equilibrium. This particle is not moving down the plane and it's not moving up the plane. So that means the frictional force acting up the plane will be equal to the only force acting down the plane, which is W sin theta. And so we can write that equation as well as F is equal to W sin theta. We also know that the relationship between the frictional force and the normal reaction is given by F is equal to mu R, where mu is the coefficient of friction between the particle and the plane. I can now substitute R into this equation here. And if I do that, I'm going to get F is equal to mu W cos theta. So if I label this equation 1 and label this equation 2, I can now solve equation 1 and equation 2 simultaneously by eliminating F, and that means equating them. So if I do that, I'm going to get mu W cos theta is equal to W sin theta. If I rearrange and make mu the subject, I'm going to get mu is equal to W sin theta over W cos theta. So I can cancel W and W over here. And so mu now is equal to sin theta over cos theta, which is tan theta. And that is the proof required. B refers to the particle in part A. So I'm going to reproduce this diagram and proceed from there. So that is the diagram produced, this time without the frictional force, because there will be a change of frictional force. The question states that equilibrium is limiting with Q on the point of moving up the plane. That means F will now act in the opposite direction as follows. I've labeled it F1 to differentiate it from the first friction, because this friction is new and is different from the friction here. There's also a horizontal force, P, acting that way. So these are all the forces acting on the particle now. We now need to resolve all the forces that are neither perpendicular to the plane nor parallel to the plane. The normal reaction is perpendicular to the plane, so we don't need to resolve that. The frictional force F1 is parallel to the plane, so we don't need to resolve that. So the two forces that we need to resolve are the weight W and the new force P. W has already been resolved, and we get W cos theta and W sin theta. Now we can resolve the horizontal force P as follows: perpendicular to the plane and parallel to the plane. This angle here and that angle here are alternate. That means this angle is theta, and this angle is 90 degrees. So we can use SOHCAHTOA to find these components here. So the perpendicular component is P sin theta, and the parallel component is P cos theta. We can now proceed to write equations as follows. The particle is not flying off the plane, it's not moving through the plane, so it means the forces acting this way must be because the forces acting downward this way. And that means the normal reaction will be equals to P sin theta plus W cos theta. So we can write that the first equation as R is equals to P sin theta plus W cos theta. So that's the first equation. Now, the forces acting parallel to the plane are also in equilibrium, and that means F1 plus W sin theta will be equals to the only force acting up the plane, which is P cos theta. And so we can write P cos theta is equals to F1 plus W sin theta. Now I'm going to rearrange this equation and make F1 a subject. So if I do that, I'm going to get F1 is equals to P cos theta minus W sin theta. We also know that the relationship between the normal reaction and the frictional force will be given by F1 is equals to mu R. And again, the normal reaction here will be different from the normal reaction right here. So let's change all that to R1. So we can change that to R1 and that to R1. So we can change that one to R1 as well. So now I can substitute this value of R1 into this to get this equation here. F1 is equals to mu brackets P sin theta plus W cos theta. So now we can see that we've got two equations for F1. There's one here, there's this one here, and the other one here. We can eliminate F1 then by solving the two equations simultaneously, and we can do that by just equating them. So if I do that, I'm going to get mu brackets P sin theta plus W cos theta must be equal to P cos theta minus W sin theta. But mu is a property of the particle and the surface. It's the same surface and particle in the part B of the question, so mu remains the same. We found mu to be tan theta, so we can replace mu with tan theta. And so if we do that, we can get tan theta brackets P sin theta plus W cos theta equals to P cos theta minus W sin theta. But we know from pure maths that tan theta is equal to sin theta over cos theta. So I can replace tan theta with sin theta over cos theta. So I get sin theta over cos theta brackets P sin theta plus W cos theta equals to P cos theta minus W sin theta. I can now take cos theta to that side, and I'm going to get sin theta brackets P sin theta plus W cos theta equals to cos theta brackets P cos theta minus W sine theta. If I expand both sides of the equation, I'm going to get P sine squared theta plus W sine theta cos theta equals to P cos squared theta minus W sine theta cos theta. I'll bring like terms together involved with W and the P. That means I'll bring minus sine theta cos theta over here and take P sine squared theta to that side. And I'm going to get W sine theta cos theta plus W sine theta cos theta equals to P cos squared theta minus P sine squared theta. If I simplify this, I'm going to get 2 W sine theta cos theta equals to P brackets cos squared theta minus sine squared theta. I'm now going to rewrite this again in a different way as follows. W brackets 2 sine theta cos theta equals to P brackets cos squared theta minus sine squared theta. Now, from pure maths, we know that sine 2 theta equals to 2 sine theta cos theta. We also know that cos 2 theta is equal to cos squared theta minus sine squared theta. So I can replace this with sine 2 theta and replace this with cos 2 theta. So I'm going to get W sine 2 theta equals to P cos 2 theta. Now if I make P the subject, I'm going to get P is equals to W sine 2 theta over cos 2 theta. But we know that sine 2 theta over cos 2 theta will be equals to tan 2 theta. So P therefore becomes W tan 2 theta. And this is the required ratio between P, W, and theta. Question 2. A particle of mass 2 kilograms is moving down a rough plane that is inclined at an angle theta to the horizontal, where tan theta is equal to 3/4. A force T newtons acts horizontally on the particle towards the plane. Given that the coefficient of friction is 3/10 and that the particle is moving at a constant velocity, calculate the value of T. So we have to do a sketch as follows. This is the horizontal ground and this is the plane, which is inclined at an angle theta to the horizontal. And this is the particle, which has a mass of 2 kilograms, which means that the weight will be 2 g newtons acting downwards. Now the particle is on a plane. That means there will be a normal reaction force perpendicular to the plane. We also know that the particle is moving down a rough plane. So because it's moving down, friction will be acting in the opposite direction. There's also a force of T acting horizontally on the particle towards the plane. So these are the forces acting on the particle. We now have to resolve all the forces that are neither perpendicular nor parallel to the plane. We do not have to resolve the frictional force F because it's already parallel to the plane, and we do not need to resolve R because it's acting normal to the plane. So the two forces that we're going to resolve are the 2g Newton force and the T Newton force. We can resolve the 2g Newton force as follows. Perpendicular to the plane and parallel to the plane. This angle here is theta, and so we can use SOHCAHTOA to find this component of the force and that component of the force. And we are going to get 2g cos theta perpendicular to the plane and 2g sin theta parallel plane. Similarly, we can resolve the T Newton force as follows: perpendicular to the plane and parallel to the plane. But this angle here is theta because this angle and this angle are alternate angles. But this angle here is 90 degrees. We can now proceed to resolve this force as follows: T sine theta, which is perpendicular to the plane, and T cos theta, which is parallel to the plane. Now we are going to use Newton's second law of motion to solve this question. Newton's second law of motion states that force is equal to mass times acceleration, where F is a resultant force moving this particle down the plane, and M is the mass and A is the acceleration. For this particle, the resultant force moving the particle down the plane will be given by 2g sine theta, which is this force here, minus the frictional force minus T cos theta, because they're going the opposite direction. So that would be minus F minus T cos theta. And so that should be our resultant force, F. The mass is equal to 2, and the acceleration is equal to 0. The acceleration is equal to 0 because it says here that the particle is moving with constant velocity. So when a particle is moving with constant velocity, it is not accelerating. We can now do our substitution into Newton's second law of motion, which is F equals to ma, and we are going to get 2g sine theta minus F minus T cos theta is equals to 2 times 0, which means 2g sine theta minus F minus T cos theta is equal to 0. I'll now make the friction the subject, and I'm going to get F is equals to 2g sine theta minus T cos theta. At this point, we can find the exact values of sine theta and cos theta by drawing a right angled triangle like that. That would be 90. And if I put theta here, I can say this is 3 and this is 4, because we are told that tan theta is equal to 3 over 4. And if I use Pythagoras theorem, I can get this length to be 5. I can now write sine theta as 3 over 5 and cos theta as 4 over 5. So I can do my substitution into this equation here as follows. F is equals to 2g times 3 over 5 minus T times 4 over 5. That gives me 6g over 5 minus 40 over 5. So F will become 2 over 5 brackets 3g minus 2t. Now we also know that the particle is not flying off the plane or moving through the plane. So it means that perpendicularly, the particle is in equilibrium. That means that R will be equals to T sine theta plus 2g cos theta. And so we can write R is equals to T sine theta plus 2g cos theta. We can go ahead and simplify this equation by doing our appropriate substitution for sine theta and cos theta. So I'm going to get R is equals to T times 3 over 5 plus 2g times 4 over 5. That will give 3t over 5 plus 8g over 5. R will become 1 over 5 brackets 3t plus 8g. But we also know that the relationship between the friction and the normal reaction is given by F is equals to mu R. It is given that mu is 3 over 10. And now we know that R is given by 1 over 5 brackets 3t plus 8g. So we can do our appropriate substitution as follows. F is equals to mu, which is 3 over 10, times R, which is 1 over 5 brackets 3t plus 8g. That will be equal to 3 over 50 brackets 3t plus 8g. So we got F equals to 3 over 50 brackets 3t plus 8g. We also know that F is given by 2 over 5 brackets 2g minus 2t. So we can solve this equation and that simultaneously by equating them to eliminate F and solve for t. So if we do that, we're going to get 3 over 50 brackets 3t plus 8g is equal to 2 over 5 bracket 3g minus 2t. I'm now going to multiply this term and this term by 50. And then if I do that, I'm going to get 3 brackets 3t plus 8g equals to 20 brackets 3g minus 2t. I can now expand to get 90 plus 24g equals to 60g minus 40t. I can now solve for t by taking minus 40 to this side and plus 24g to that side. And I'm going to get 90 plus 40t is equals to 60g minus 24g. That will be 49. T is equals to 36g. So T will be equals to 36g over 49, and that will give me 7.2 newtons. And that is the value required for T. And this brings us to the end of this session on forces and friction.